Hey everybody, I wanted to record a quick video of me solving one of the practice problems that I just sent you. So it's number 6, where we have a big concrete cylinder that for some reason is attached to this 2,000 kilogram mass, and they're both moving at 20 meters per second to the right initially, and obviously the cylinder is rolling. There's no friction acting on the cylinder, but there is on the mass because it's sliding along the ground and the coefficient of friction is 0.2. And we have the mass of the cylinder, its radius, and since it's a hollow cylinder, its moment of inertia is just mass times its radius squared. So the question is, after these roll for 44 meters, or after this rolls and drags this along with it, how fast are they going? All right, so for pretty much all work and energy systems, our strategy, we can pretty much use the same strategy. In this based on conservation of energy, right? So energy is always conserved. So it's kind of like saying the energy at the beginning plus any energy added will equal the energy at the end, right? Or it's like saying the energy at the beginning minus any energy lost will equal the energy at the end, right? So we just break that up into point A, total energy of the system at point A, plus any work added or lost from A to B is going to equal the total energy of the system at point B. We ask what types of energy exist at each point, and then we just add them up to find the total. All right, so in our case, we're going to say, okay, let's think about the beginning as point A when we have our initial velocity given. And after we've traveled 44 meters, that's point B. So what types of energy do we have at the beginning, right? So we can think about spring energy, potential energy, kinetic energy. Now we have to think about rotational energy too. All right, so this is a problem where we're not really changing in elevation, so there isn't going to be any change in potential energy, so we don't need to worry about that. And there's no springs or anything, so all we have is the kinetic energy of the block, the kinetic energy of the cylinder, and the rotational energy of the cylinder. So we would just add all of those up to get the total energy at point A. And what types of energy do we have at point B? Well, this is a pretty simple situation where actually the types of energy are going to be the same. This is still going to be rolling along, so we'll have rotational energy, and we'll have the kinetic energy of the cylinder, and the block will still be sliding and moving, so we'll also have the kinetic energy of the block. So exact same types of energy at point B in this case. And then what energy is added or lost? Well, friction, right? So this friction force is kind of dragging this block this way in the opposite direction it's moving. That's going to be slowing it down. It's doing work on this block, and that's going to remove energy from the system. So we're going to need to think about the work done by friction. And the work done by any force is the magnitude of the force times the displacement times the cosine of the angle between the force and the displacement. And in this case, the displacement, or the direction the block is moving, is opposite the direction that the friction force is pointing, right? The friction force is pointing in the opposite direction of the velocity. So that makes the angle between them 180 degrees. Cosine of 180 degrees is -1. So pretty much it'll always be the case that the work done by friction will be negative the magnitude of the friction force times the displacement. And remember, the magnitude of the friction force is equal to the coefficient of friction times the normal force, whatever the normal force on that object may be. All right, so we can start plugging in some numbers now, right? We have our equation for the total energy at point A, kinetic energy of the block, kinetic energy of the cylinder, and the rotational energy of the cylinder. And we just need to make one quick substitution for the rotational velocity. Remember, the rotational velocity is going to equal the translational velocity divided by the radius. And it's given that the moment of inertia of this cylinder is mr squared, so we plug that in and get those numbers. And we add things together and turns out 640,000 joules. That's our total energy at point A. And then we could say, what's the work done by friction, right? So it's going to be negative, and then 0.02, that's our coefficient of friction. In this case, the block is just sitting on the ground. Gravity is acting on it, so the normal force is going to be opposing gravity. So the normal force in this case is just going to be the mass times gravity. And then the displacement is 44 meters. So we add all that together, we get that the work done by friction is negative 172,700 joules. So remember, the total energy at B is just the energy at A plus any work that's done in between A and B. So we are just going to take 640,000 joules and subtract 172,700 joules. So we get the total energy at B is equal to 467,300 joules. All right. And now we write our equation down for what types of energy exist at B. And in our case, it was fairly simple because it was the same types of energy at A: kinetic energy of block, kinetic energy of cylinder, rotational energy of block. Except now the velocities are unknown, right? Because that's what it's asking. How fast are we moving? So we make this quick substitution again for the rotational velocity. Rotational velocity squared is going to equal the translational velocity squared divided by the radius squared. And the moment of inertia is going to equal mass times radius squared. So you can see radius squared is going to calculate with radius squared there. And what you're left with is actually, look, you have 1/2 mass times v squared. And that so happens for this one, it's exactly after the radius cancels, it's exactly the same. Sorry, it's exactly the same as the kinetic energy equation. So we have two 1/2 mv squareds for the cylinder. They add up to 1. And after we plug in the masses and then simply take the, divide through and take the square root to find the velocity, we find the translational velocity is 17.09 meters per second. All right, hopefully that clarifies some things, right? If you kind of just follow this process, right, total energy conservation, right? Energy at the beginning plus energy added is equal to the energy at the end, right? Or energy lost, right? And then you say, what types of energy do we have at each point? Maybe it's point A and then point B and then point C. You do the same thing. And since energy is a scalar, we're just adding the different types of energy of the system together. And remember, it's the energy of the system that counts. If you have more than one object, you need to think about the total energy of the system. Alrighty. Thanks for watching. Talk to you soon.